This is my presentation for Lab 2. The goal of this lab was to analyze the effects of gravity and drag forces on a falling object. The main principle I studied in this lab was Newton's second law, which I use in my computational models to predict velocity and position by calculating net force. To find the net force in the system, I had to calculate both gravity and drag forces. Gravity, also known as weight, is found by multiplying mass by the gravitational constant g, which for our context, studying an object on Earth, is 9.8. The force of gravity is always in the negative y direction, which is why the negative sign and j hat are included in the formula. In the second part of the study, I had to take into account drag, which is the force that acts in the opposite direction to the object moving through the surrounding fluid. In this context, the surrounding fluid is air, and we know that the direction of the drag force is in the positive y direction because our studied object is falling in the negative y direction. To get drag, you have to multiply velocity by -1 and the drag constant b that depends on the size and shape of the object. And as I said, to get the net force, we have to add these two forces together. I chose to observe a frisbee because I thought the weight would be evenly distributed enough to fall in a straight line, and that its dish shape would experience the effects of drag even at a low speed. So I analyzed the video and tracker and decided to track position up until this point a little before it hit the ground. And this is my first computational model in which I plugged in all the necessary components, such as initial position at 3.67 meters and initial velocity at rest. For this model, I only included gravity in the net force interacting with the frisbee to see how much the drag force did or did not impact it. And this is the comparison between what the model predicted in blue and the observed position in red. As you can see, they are very similar towards the beginning, but the variance continues to increase over time. At the end of the time frame, the predicted position is closer to the ground than the observed position. So I created a second model, this time including drag, to more accurately predict the motion of the frisbee. For this model, I included the drag force and the net force, and for the drag formula, I made the magnitude proportional to the square of the object's speed as instructed. For the drag constant, I experimented with different values to get a more accurate prediction. So these are all of the models graphed together. As you can see, the new model included the drag force is in yellow, and it follows the observed position much more closely throughout the entire time frame. So in conclusion, these comparisons tell us that the effects of drag on the frisbee within this time frame are small but evident. We also know that the higher the speed of the frisbee, the larger the effects of drag, because in the graph, the space between the gravity position line and the observed position got larger over time. We also know this because in this formula we use for turbulent drag, the magnitude is proportional to the square of the object's speed. Lastly, there are two questions to address. The first is which model, if any, predicts terminal velocity. That would have to be the gravity plus drag model, because over time, the drag force increases and cancels out the force of gravity to reach a zero net force, causing a constant speed at terminal velocity. The second question is what if the object was initially thrown down, and would that change the terminal velocity? To address this question, I use a glow script. The first graph shows the gravity plus drag model, but tracked over a longer period of time, which is 3 seconds. On the right, I modeled the system with an added initial push by changing the initial velocity in the code to -3 in the y direction. By comparing these graphs, we can see that we get the same terminal velocity, because if we compare the portions of the graph where they turn into straight lines, we get the same value for the slope, which is equivalent to the velocity of the falling object. The only difference that can be seen is that with the initial push, it took less time to reach terminal velocity. Because the drag force changes over time to counteract the force of gravity and any initial push, big or small, the falling object will always return to the same terminal velocity.